This is in the base side. I have applied the Kirchhoff's voltage law equation. Any doubts you have in this two equations, what you have seen here? You have to be very, very strong in KVL. And you should be able to apply KVL very, very quickly when a circuit is given. You have to apply KVL at the input side. Input side is base. Output side is collector. If you can apply KVL instantly by seeing a circuit, then it will be very, very interesting to explore these circuits with mathematical equations. Okay. So having derived the expression for IB and RB using KVL in the base side, now I am going to go in this. Now I can apply KVL in the collector side also. So if I apply collector in KVL in the collector side, I will be using this path. So in this path, how many voltages you have? How many voltages you have in this new path, what I am showing in the output side? Same way, you have two voltages. One is VCC, one is VCE. Okay, and VCE will oppose your VCC. So you will get VCC minus VCE equal to IC into RC. From that, I can find RC is equal to VCC minus VCE by IC. That equation is not given here, but that is the equation what you get when you apply KVL at the collector side. VCC minus VCE equal to IC into RC. So if you want RC equal to VCC minus VCE by IC. If you want IC equal to VCC minus VCE by RC. Either ways you can get the equation. And our stability factor S is going to be, see the formula for S is 1 plus beta by 1 minus beta into DIB by DIC. See the expression for IB. What can you say about the expression for IB? It is variable or constant. What can you say about this expression for IB? It is variable or constant? It is variable or constant? Yes, it is variable or constant. You are getting the question. I want to know whether the IB is depending on any parameter or it is constant. VCC is constant. VB is 0.7 for silicon and 0.2 for germanium. RB is going to be constant. So IB is also going to be constant. So if I differentiate IB with respect to IC, the answer is 0. So when you substitute DIB by DIC equal to 0 in the expression for stability factor, this expression becomes 0. So stability factor becomes 1 plus beta by 1 minus beta into 0. So beta into 0 becomes 0. 1 minus 0 becomes 1. So S is equal to 1 plus beta. Okay, so stability factor for this circuit is 1 plus beta. And beta, you know, it is very, very large. The value of beta is 140 for a normal common emitter amplifier. So the stability factor will be 141. You know, S is 1 plus beta. So it will be very, very high. But I think you have to remember that the stability factor value has to be as low as possible. I told you in the beginning, stability factor indicates variation of collector current. So the stability factor value has to be as small as possible. So 141 is a very large number. So this circuit is not going to provide me any effective biasing for my common emitter amplifier because my stability factor is very, very large. Ideally, my stability factor should be 0, but practically it can be very, very small. But here you see the stability factor is 141, which is very, very high. So therefore, this circuit is not mostly used for biasing the common emitter amplifier. Many advanced circuits have been developed which are found to be effective. So this circuit which was developed as the first circuit for biasing cannot be used because the stability factor is very, very poor. The advantage is it is very simple. You need only two components, RB and RC. With that, you can design the circuit. So if the supply voltage is very, very large compared to VBE, then the base current becomes independent. So stability factor, you know, it is 1 plus beta, right? So stability factor also you cannot improve it. You cannot reduce it because VCC is very, very large compared to VBE. So since this is the case, I cannot never even think of reducing the value of stability factor. Yes. So it will be almost equal, approximately equal to 1 plus beta only always. So you can never reduce it. So this circuit becomes an inefficient biasing circuit for common emitter amplifier.